Hello, everyone, and thanks for joining us today. My name is Bryce Babinick, and I'm a 3D printing technician here at MLC CAD Systems. And we're going to be talking about how to make the most of the Formlabs Fuse SLS 3D printer. And if you don't know what that is, that's totally fine. We're going to go through it briefly as we get started here. But what you'll probably be interested in right off the bat is what's in the first part of my title here, that I've included as sort of an attention grabber or a little bit of clickbait. But if you're like me and your previous experience with 3D printing has been in the hobbyist world or maybe even with industrial printers through work and using FDM or SLA printing, this SLS technology that the Fuse uses is just incredibly mind-blowing. And it's not just the quantities of parts that you can get, but the types of parts and geometries that you can make. There are very few limitations when it comes to SLS. And so, of all the crazy printers that we have here at MLC, I think this is the one that I want to take home and put in my garage the most. And hopefully, you'll be able to see why by the end of this thing. But let's go ahead and get into it. So, let's go through our agenda really quick, and then we'll get to the fun stuff. I'll start with a quick introduction to SLS in general, and then we'll talk more specifically about the Fuse ecosystem, what it looks like and how it all works together. I wanted to include these parts just so we're not ostracizing anyone who's not familiar with this technology, because I think it's important to understand how it all works before we talk about how to optimize it. So once we're familiar with that, we'll go through some of the key factors for getting a good cost per part, which are refresh rate and packing density. And once we have a good understanding of how everything in the physical world is working, we can jump into the slicing software. And there, again, I'll show you how to set up a build with hundreds of parts with just a few clicks and how to maximize your cost per part. So diving right in, let's look at SLS 3D printing. We'll just do a quick introduction here. I think the easiest way to understand SLS, and particularly its benefits, is to look at it relative to FDM or SLA printing, which tend to be much more common and most people have some familiarity with. Because like a lot of manufacturing technologies out there are quite a few different approaches for 3D printing, and each has its benefits, each has its pros and cons. So starting with the similarities, all three of these techniques build a part up layer by layer or cross-section by cross-section. So here's a quick example of what I mean. We start at the bottom, we work our way up, and we create our part this way. Getting more specific, FDM or fused deposition modeling uses thermoplastic materials. And these printers we work with at MLC, we can even embed carbon fiber into our parts so we can get an incredible strength to weight. The material is melted and extruded from a hot nozzle, which is moved around using motors and belts and pulleys. And in simple terms, it's a robotically controlled hot glue gun. So FDM tends to be a bit easier to use, but it has a rougher surface finish, and typically you can see distinct layer lines. Nothing too crazy, especially with these sort of matte finishes where we've got chopped carbon built in. But you can see it a bit more than SLA printing, which uses a liquid resin material, which is solidified through curing. So the curing is typically done by a laser or a high-powered light, just some type of UV, and it chemically bonds the resin molecules together. And most industrial SLA printers, like the ones that we offer from Formlabs, have a huge material library, so you can make ultra-stiff glass-filled parts, all the way down to the softness of silicone, and they even offer specialty resins like castable wax or flame retardant resin. So the downside of SLA is that there are typically a few more steps, like once the part is finished, you want to take it through and wash any excess resin off of the part. And a lot of the time, you'll want to take it to a final curing step for the full mechanical properties of the part. But it does have a really, really good surface finish, and you can get some super intricate geometries. So really, between the two of these, they're incredibly useful, and you can get some super impressive parts off of it. But there is a common issue with both of them when it comes to a part's geometry, and that common issue is with overhangs. Overhangs are features on a 3D printed part which extend outward at an angle from the vertical axis. So it's kind of a mouthful, but when it comes to 3D printing with FDM, this part we would probably want to print in a different orientation, but for the sake of this explanation, we're starting at the bottom here. And then once we reach this point, we're going to have some issues because we're working with a thermoplastic, which is viscous when it first comes out of the nozzle. So if we were to print it in this orientation, it's actually going to start to sag right here because we're printing in thin air on both sides, and then the subsequent layers that go on top of that are going to sag as well. With SLA, the problem is similar, but we're typically printing upside down because we're dipping into a tank of liquid resin. And in this case, we're actually peeling the part off of that tank between layers. So there's that extra sort of suction force that's pulling it downward, and now we've got this warp in a different direction. And so it's not a huge deal at the end of the day because we can use what are called supports. And so supports just print an extra little structural piece underneath any overhangs. And once we're finished, we can rip those supports off. So this is an example for FDM. And we print these sort of zigzags. And then between the part and the support, it prints a little bit thinner so we can rip it right out. With SLA, the supports look a little bit different, but the process is pretty much the same. We're going to rip these things off. And with SLA, we can typically get away with a bit more intricate features, but in either case, the underside or the supported surface won't have quite as good of a surface finish as the rest of the part. So there may be some type of post-processing needed for this. But in addition to that, the overhangs make it so that your upper Z direction or the upper area of your print volume all of a sudden becomes a bit less useful because you're only really using it if you're printing, super tall or really big parts. Because you can cover the entire build plate in multiple parts, through the X and Y plane. But realistically, you're not going to put, parts above other parts because then everything is covered in supports. And that is really one of the biggest benefits of SLS printing. So SLS stands for Selective Laser Sintering. And now instead of a spool of plastic or a liquid resin, we're using plastic, which is melted, powdered plastic, which is melted by a laser. And with SLS, your entire print area is covered with powder during printing, and your part is printing inside of that powder. So now it's completely supported in every direction. And then once the print is finished, you remove your part from the powder, and any of the powder that didn't turn into part is recycled back into the system. So you're reusing your supports essentially. And so the main thing that means is, you don't have to worry about overhangs anymore, which, as you can imagine, opens up a huge amount of possibilities for super intricate and crazy geometries. All kinds of lattice structures and all that stuff all of a sudden becomes printable. And parts have a super good surface finish everywhere because there's no supports. And they're also bonded very strong between the layers, even more so than FDM. And it's also incredibly accurate. So that's all huge. But there's an extra benefit here, which is that your Z height all of a sudden becomes much more useful because now you can stack parts in all 3 dimensions and you can produce these huge quantities at one time. So to add to that, it's a super fast way to print things. You're printing entire layers in just a couple of seconds. So here's a quick example, and hopefully you can start to see why this technology is such a game changer in a lot of ways, and it's really the start of what mass production will be in 3D printing. So here's our layer finishing in just a couple of seconds, and then we roll across a new fresh layer of powder, and we start melting the next layer, which fuses to the previous layer, and so on, and it does this until you complete your part. So we can even see where we're at within this build right here in this little thumbnail. And there's a ton of really cool sample parts out there for SLS because of how capable it is. But if I had to show you just one, I think this is probably one of the best examples because this thing, it shows all kinds of movable parts and features and tiny things and lattice structures and whatever. And it's just wild to be able to see because when it comes to SLS, really, if it fits within the print volume, you can print it no problem and you don't have to worry about it. There's obviously a couple of small caveats there, like you don't want to be so thin that it's not strong enough, but in general, this machine is going to be able to handle anything that you throw at it. So that's a quick introduction to SLS in general, but let's take a quick look at the Formlabs Fuse specifically. And because this is about making the most of the Fuse, we'll talk about the whole supporting ecosystem as well, because these additional machines are really the first step to making the most of the Fuse because they significantly reduce the amount of operator time and time that you're going to be spending getting the parts out of the powder and mixing the powder and all that type of thing. And I won't do a full breakdown because we've already got a couple of videos over that, but I do think it's important to discuss the machines and how they work, because it'll also help us later on in our discussions in this webinar. So starting with the Fuse and some of the highlights here, it's one of the most affordable and capable SLS printers to date, and it has everything from built-in AI for print quality tracking and cloud connectivity for remote printing and monitoring, and even a built-in maintenance tracker. So this thing is really built for serviceability, and it's meant to be a workhorse and just run nonstop. So it's awesome to see these things, especially a bunch of them lined up next to each other. And one of the other cool things about the Fuse is that it's one of the first SLS printers that doesn't need an inert environment to print. And you can hook it up to nitrogen, and that may give you some benefits with certain types of materials and better refresh rates, but typically you're just going to run this thing in ambient air. So obviously there's a ton of stuff to talk about here with the Fuse, but one of the best things about it is actually on the inside, and it has to do with this build chamber. So in most SLS printers, the temperature on the inside of the chamber during printing is absolutely critical, and that's the same for the Fuse. The plastic powder is heated to just below the melting temperature, and the laser is used to selectively sinter or melt the powder together and create a part. So if there's any variability in the temperature of the powder, it may not melt thoroughly, or it may melt too much, and your parts could warp and start to have surface defects. So it's really important to keep that stability during printing, but it's also important during cooling. Because if you were to just extract your part right away, the same thing's going to happen. You're going to have different warpages and curling, and your parts might even crack. So the surrounding powder is really important, even during cooling, because it keeps the part into shape, and it also sort of insulates it, which is great, except for most SLS printers, you recapture your powder within the same device that you print with. And so the printer is down and unproductive during the entire cooling process, and that can take up to 14 hours in the Fuse. So Formlabs actually decided to separate the powder reclamation from the printer, and that's how we take advantage of this removable build chamber. So we can actually pull this build chamber out once we're finished printing, and we can set it aside to cool in the sift, and then we can add a new build chamber right away into the Fuse and kick off the next print. So that's step one of making the most of the Fuse, is to have a couple of build chambers that you can rotate between, and try to set up your schedule where you can rotate these during the workday. You don't have to go up there in the middle of the night or something crazy. And that way you're maximizing your productivity, minimizing the downtime for the printer. So that leads us into the sift, which is where your chamber will end up once it's cooling, or even during cooling. You actually use this same plug and you plug it into the sift, and there's multiple temperature sensors inside of the build chamber. And so the sift is able to track the temperature and let you know when it's safe to remove parts. And when it is, the build plate rises up and you move this whole chunk of powder and parts over, and any of the unused powder falls down through a mesh filter into a hopper. You separate your parts out, and then there is another hopper on the other side for new powder, because the powder does degrade a little bit each time it goes through this heating and cooling cycle. And so you want to mix a little bit of new powder with the used, and the sift controls that. It's called the refresh rate. It's the rate of new powder to use, and we'll talk a little bit more about that later, but for now just know that it's able to have those two places to put the powder, and the sift knows how much of each is in there, and it'll kind of give you warnings and help you set your refresh rates. So moving on to the last piece of the system, the blast is something that I didn't really know we needed until I started working with SLS. And it's necessary because unless you spend a ton of time in the sift, you're not going to get every single little bit of powder here, or you're going to spend a really long time trying to get every nook and cranny. So a blasting cabinet is important to be able to blast off just that light layer of powder that might be left on your parts. And that's actually one of the biggest pieces of advice I have. In the beginning, I spent so much time trying to get every nook and cranny brushed off and cleaned to try and save that powder, but realistically, the amount that you're saving and reclaiming isn't that much, and the amount of labor that you spend trying to get those parts super clean is worth quite a bit more than that in most cases. So Formlabs' own recommendation is to get parts looking roughly like a potato, where you can sort of start to make out the part, but save the nooks and crannies for the blast. And initially we didn't have the blast from Formlabs because it didn't exist yet. And I found out how difficult it is to hit a part from every single angle to make sure it's fully clean. And not only that, but you're picking up each individual part and rotating it one at a time. So it takes quite a while to get these things blasted off, but the blast solves all that because it has this rotating drum with automated blasting cycles. So you spend just a few minutes in the SIF now, and then you bring it over to the blast, you put your parts inside, and then you just walk away. It's got its automated cycle that it'll run through. And then the second great thing about the blast is it eliminates a whole other step, which is before we had the blast, we had to clean the parts off even after they were blasted because they're covered in blasting media. But the blast has a deionizer built in, and that just keeps the blasting media and the powder from sticking to the part. So they are white glove clean, ready to go right out of this machine. So it's also got a polishing option coming in the future, and that's really exciting because we're getting injection molded looking parts right out of this machine that don't even look 3D printed. So awesome to see that, and we're looking forward to it. All right, so let's finally discuss packing density and refresh rates, because this is where you really start to maximize your cost per part when it comes to SLS. So we touched on this earlier, but to recap, refresh rate is the minimum ratio of fresh powder that's mixed into used powder for continued printing and to retain the material's mechanical properties. So the recommended refresh rate depends on the material that you're using and whether you're printing in air or using nitrogen. Nitrogen can improve the dimensional accuracy, but it doesn't necessarily significantly affect the material properties or even the print success. So generally nylon 12 is our most popular powder, and it's what we typically use, so I'll focus on that going forward. It has great material properties, great physical properties, and it has a really good refresh rate even in air. So we'll stick with a 30% refresh rate for the rest of our discussion as well. And a lot of SLS printers require manual measuring and mixing of new powders to used powders. But fortunately, we have the SIFT, and it manages that for us. There's an interface built in, and we can select our desired refresh rate, and the machine will automatically dispense the appropriate amount of powder, and then you can mix it using the machine as well. So here's a quick clip to give you a look at what that process looks like in this. And so this is where it mixes. We've got our used hopper on the left and our new hopper on the right. So this is our new powder coming in. It drops into a cartridge. We mix it in this cartridge using a mixer on the side of the SIFT, and then we move it back over to the printer for use in the future. So packing density is relatively straightforward at a glance, but it can be a commonly overlooked characteristic when it comes to SLS, and it can get a little bit confusing because of the variability. So I'll spend a little bit of time here. And so off the bat, packing density is the percentage of fused part in a build relative to the total amount of powder used. So basically the percentage of part to powder in a build chamber. And when it comes to the fuse, our ideal packing density is an average of at least 30% part to 70% powder. If that number looks familiar, there's a reason, and it's because that number is, we really want it to at least match our refresh rate, because if we're using 30% of the powder in the chamber, that 30% is being replaced with new powder. And if we're using more than 30%, it's even better because we'll end up with an even higher refresh rate. So we've got lots of fresh material mixed in with the used. And if that's confusing, that's great because it justifies the embarrassing amount of time I spent on these next few slides. So let's visualize this process just to make sure we all get it. So here we've got our fuse on the left, which is full of fresh powder. We've got 10 blocks here, so each block represents 10% of our volume. And on the right side, we've got some representations for our used powder hopper and the fresh powder hopper within the SIFT. So let's kick off a print that has a 30% packing density. So we heat it up, and now we have our fused powder in yellow in red, and then we have our used powder in yellow. So we take this over to the SIFT, we get our parts out, and we're happy with those. We take them away for the blast. But we end up with this amount of used powder in the used powder hopper, which is fine. We're going to use our 30% refresh rate, and we're going to be able to use all of our used powder each time we go through this build. So another quick example using 50%. Same process. We've got our parts out, and now we're only partially able to fill the used powder hopper. And if we were to use that same 30% refresh rate, we actually wouldn't be able to fully fill the sift the next time, but that's totally fine. Uh, we can either use a 50% refresh rate, or we can do our 30 and then just top it off with fully fresh powder. The problem is when you start to get to those really low packing densities. So this would be a really big part, or a couple of like awkwardly shaped parts that are maybe like hollow on the inside. And so the problem that we run into, we'll be able to visualize here. So we heat up this entire chamber, and we only have a little bit of parts that we're able to get out of it. And now we have a huge amount of powder, used powder in our hopper. And when we go to refresh it, that's fine. We have just a little bit left over in our used powder hopper, which again is totally fine. But if you keep going this way, you're going to end up with a lot of extra powder. So as you can see, it just keeps growing. And in the worst case scenario, it increases our cost per part, because this eventually might just become waste powder that we dispose of. So we just have to absorb that into our cost per part. But there are a few things that you can do here. And the first thing is you can try to find other smaller parts to pack into that build. So with SLS, you can nest parts inside of each other or push them right up against each other. They really only need to be about 1 millimeter distance between parts. So that's one option. The next thing you can do is offset this by coming up with a really high packing density build. So this one may only be 10%, but if we have some builds in the future that are 50 or 60%, our used powder supply is going to balance out, and that's no problem. So the next thing you can do is store up a bunch of this used powder and then save it for a prototyping build. So with nitrogen, we've seen builds as low as 0% refresh, and in air, we've seen as low as 10% refresh, where you may have a slight reduction in your part quality and your physical properties, but you can still have a part in your hand for fit and function. And then there is one last option, and this one's pretty convenient. It's that you don't have to spend as much time in the sift. So where you might normally spend 10 minutes sifting and trying to get all the media off, or all the powder off so you can reclaim it, now you only need a few minutes in the sift, and then you can let the blast do the rest of the work, which works out perfectly because the blast has an automatic powder separation. So that keeps your blasting media from degrading by being totally saturated with printing powder. And then later on, you can just dispose of that excess powder, and again, you can sort of absorb that into your cost per part. So it's really not the end of the world to end up with a low packing density, but it is something to keep in mind as you're laying out builds for the Fuse. And that's a great segue into our next topic. How do you know what your packing density is, and how do you maximize it? Well, that all happens on the software side. So let's take a look at a couple of example builds, and I'll show you what parts are a great fit for this system and how you can use the tools in the software to set up hundreds of parts in a really high packing density with just a few clicks. So I think this first example is really interesting, which is a GoPro mount for a motorcycle helmet. And you may laugh at first, but I don't just think this is cool because I made it and it's for my helmet. The reason I think it's interesting is because the problem it solves is a really good fit for 3D printing. And in fact, there's already a company out there that's sole purpose is making these for different helmets, and they're using 3D printing to do it. So the reason it exists is obviously to put a camera on a helmet, and it gives you that really nice point of view. But it's 3D printed because every single helmet out there has different curvatures to it and different shapes needed. So, for example, this one has a curvature in one direction and a different curvature in a different direction. And then on top of that, manufacturers come out with new models every few years to replace the old models. And so there's this humongous variability in the shapes and sizes that these need to be to fit onto helmets. And the existing GoPro mounts that you get with the camera don't typically work with whatever curvature is on the helmet. And so maybe you can find a spot that it would work on, but then you're using a bunch of these different adapters to get the camera positioned correctly. So 3D printing is great because it's so easy to get that high variability between parts with basically no effort required outside of adjusting your CAD model, which you would have to do anyways if you were manufacturing this part traditionally. So it's also a great fit because you're not going to end up with a huge overstock of parts that get outdated. You can essentially make these things to order, and you can do hundreds of the same part if that's what the demand is, or you can do different parts, hundreds at a time of each of them, for different helmets in the same build with the same machine and the same footprint. So no storage needed for multiple injection molds and all the associated tools. It really simplifies things for this workflow. So before I keep going on that tangent, let's go ahead and set up a few of these within Preform, and I'll show you how to do a few hundred. So here's Preform at a glance. We have our build chamber for the fuse laid out here, and we can start putting our parts inside of it. And then on this side, we can select the type of printer we're using, the material we're using, and then we can start to play around with our print settings. The speed optimized setting for this part is going to be no problem because it's not a super complicated part, and that actually controls the way that the laser lays the part out. And so again, for relatively simple models, the speed optimized is no issue. So now the next step is to just drag and drop our STL file. And then I'm actually going to drag this thing into the corner over here and start using the tools in Preform to build out our full build here. So one of the most convenient ones is this Array Models tool. And so this starts expanding out in all 3 dimensions. And by default, they give you this 5mm spacing, which is super safe, but we can go as low as 1mm here with no issues. So I'll go ahead and do that in the 3 directions. And then this is the way I like to do it. Expand it out and see, okay, we've still got a little bit of room here. So I'll go ahead and add an extra millimeter just to be safe. And then same thing in the Y direction. Got a little bit extra, so I'll expand it out one more. And then let's grow up in the Z. And let's see how much space we have there at the top. Same thing, we've got some space there. So I'll add a little safety buffer of 2mm. And now we've got 320 of these models built out in our chamber here. And calculating the time for these can take a little bit, so I went ahead and pre-calculated it. So we've got 16 hours to print 320 of these things. And after 16 hours, we can go ahead and pull this chamber out, put a new one in, and kick that next one off. And we'll leave this chamber, the first chamber, cooling for 13 hours, 14 hours in the sift. And once it's ready, we can go ahead and pull all these parts out and they're ready to go. Our packing density is 40%, so we're golden there. We're above our 30% refresh rate. And so we're going to be able to have a really good refresh rate going forward, and we're getting good quality parts. So the total powder used is 5.42 kilograms, but the number we're actually kind of concerned with here is 2.17. That's the fused powder that actually becomes part. And I did these calculations beforehand. The fused powder comes out to $216.64 roughly for this whole build. So we divide that by our 320 parts, and we get about 68 cents for each one of these things. And I've seen these things go for $20 or $30, so we're making pretty good profit here. So again, a pretty cool example of this, and a good one for SLS. But let's take a look at a couple other things now too. So moving on to our second example build, this was sort of inspired by a customer that came to us that was actually looking to have some test prints done to see if the system would work for them. And they had these really interesting sort of spacers and some type of like crush washers that they were using for oil and gas. And so I kind of recreated, I didn't want to use their exact parts, so these are just sort of recreations. And at first they wanted to just have an idea of what high volume build would look like for each one of these. But as we were going through it, we realized that these parts actually fit inside of each other. So we can get a much better packing density if we print them all at the same time and just nest these parts inside. So taking a look at the build, we're going to use a couple of little tricks here by taking advantage of the array tool once again. And so in this case, we can actually stack up some of these parts within the group here. And so we can put 4 more of these, so we'll apply that. This one we can double up as well. And so we'll drop that to 1mm. We'll get rid of these guys, we'll bump it up. And so now we've got quite a few of each one of these. And then again, we can start using some different tricks here. So we could array this thing out, but notice that we can't increase it any more than this. So this would be just 4 parts, but we're not quite meeting our packing density yet. So we're gonna have to use another trick, which is just being a little bit smarter than the system here. And we can start to move all these parts into the corners. And now we've got space in the middle for one more, so we can just create a duplicate. I'll go ahead and slide this one over to the middle. We'll bring this guy down. And now we've got a 34% packing density. So we're looking much better here. And now we can start to array this entire group up as many as we can. And now we've got 600 parts. So there's varying numbers of each one of these things, but we can basically split up our cost per part, and it's going to be the same for each one technically after this full build. So again, I've pre-done this one just so we can have the print times, which is 15 hours and 40 minutes. Chamber cooling is, again, pretty similar, 13 hours and 51 minutes. And now we've got our packing density of 33%, so we're good to go there. And fuse powder, 1.63 kilograms. And so looking at this one on the calculator, the entire build is $162.73. So divided by our 600 parts, we're looking at 27 cents for each one of these things. So definitely dropping our cost per part down here with such high quantities and still meeting our packing density. So now let's take a look at one more example and we'll keep moving. And our third example here is a bit of a fun one. It's just an example to show the absolute chaos that you can get away with when it comes to SLS 3D printing, because you can just get away with printing anything basically and know that it's going to come out just fine. So we've got this random assortment of parts. In our case, this happens occasionally if we end up with a bunch of excess powder, or we need to come up with a bunch of demo parts to give away for an event or something like that. But in the real world, it may happen where you're in the shop and you have requests for a bunch of random parts, or you have some type of 3D printing shop where you sell these things directly and all the requests come in for these different parts. And so you need to lay out a bunch of stuff at one time. And so here's a quick way that you can do that and get it all set up very quickly and easily. So in this case, I just dragged and dropped all of these STLs into Preform, and I can come in here and I can start creating duplicates of maybe the parts that we need a couple of. So in this case, I'll create a couple of these guys. Maybe a couple of these generative handles. This thing is pretty cool. It's like a print in place piece. These rooks are very interesting. This pipe fitting here, create a handful of those, and then at the end of the day I can come in here and I can just select all of these parts, and there's this built-in button where I can just pack everything together 1 millimeter apart. And so a lot of the times if you're in production, you want everything oriented the same for consistency, but in this case we're not too worried about that. We just want to kick everything off and let it print. And there we go. We've got this thing packed way down into this tiny little section here, and we're pretty close. We've got 25% packing density. So if we wanted to bump that up, we could just keep adding some of these smaller parts and letting it repack, or manually kind of sliding them in wherever they fit. So just a cool example to end it off and to show one of the last really interesting tools that we can use here. So that concludes today's webinar, but feel free to stick around if you have questions. We'll be happy to hang out and answer them with you guys. Or if you're watching this on YouTube later, please leave a comment and we will get back to you whenever we can. But thank you guys for watching today. Hope you enjoyed it, and have a good rest of your day.